Hello everyone, welcome back to the Distributed Generation and Smart Grid lecture series. In this video we are going to discuss about another kind of distributed energy resources, solar photovoltaic systems or PV systems. Solar PV generation involves the generation of electricity from a free and inexhaustible solar energy. As you all know that there are many advantages of a PV systems, mainly like a sustainable nature of solar energy, then minimum environmental impact, drastic reduction in the customer's electricity bill due to the free availability of sunlight, long functional lifetime over 30 years with minimum maintenance, and the silent operations. So owing to these benefits, today PV systems are recognized by governments, environmental organizations, and commercial organizations as a technology with the potential to supply significant part of the world's energy needs in a sustainable and renewable manner. So one day of sunshine could supply all the world's energy for 4 to 5 years. So the sun's full intensity and brightness is 1000 watts per meter squared. So this intensity can be diminished according to the climate and site specific conditions. And peak sun per day is about 5 hours between 10 a.m. and 3 p.m. During that period we can generate the peak power. And a solar cell is the smallest unit of the PV system. There are two types of manufactured PVs, like a silicon cell or amorphous silicon. In the structure of or anatomy of a solar cell, boron is used for the positive layer and phosphorus is used for the negative layer. The photons generated from sun energizes and knock the loose extra phosphorus electron which crosses the p-n junction to fill the hole on the boron atom. The energy released in the process produces 0.5 volt of direct current. So this is a photovoltaic effect, a pictorial representation. So whenever light incident on the material, you can collect the electron through the external load circuit. It will generate the electricity. That is the photovoltaic effect. And though the PV cells can effectively used as DER or distributed energy resources in a microgrid, yet they suffer from the disadvantages of high installation cost and low energy efficiency. In case of solar energy technology, solar energy reaches the PV cell into two components, like direct and diffuse components. The direct component is about 85% and comes through the direct radiation. The diffuse component is about 15% and comes through the scattered diffusion in the atmosphere. So a PV cell effectively it can be behaves as a photodiode. So light energy incident on the cell surface in the form of photons generate the electron hole pairs as current carrier at the p-n junction. So the photocurrent produced by the PV cell is directly related to its surface area, incident irradiance, and the ambient temperature. So depending upon these three factors, incident surface area and incident irradiance and ambient temperature, And this generated voltage is limited by the forward voltage drop across the PN junction. So it's behave like a photodiode. And as the voltage and the current output of the single cell are very small, a large number of cells are arranged in a series parallel combination to produce the PV arrays. It is known as a PV array, and or it can be say modules of higher voltage and power rating. And nowadays the most PV modules are equipped with maximum power point tracking or MPPT systems that maximize the power output from the modules by shifting the operating point depending upon the solar irradiance. So with respect to the variation of the solar irradiance and temperature, the maximum power point will be changes. So it can be easily tracked by some algorithms, which is usually known as maximum power point tracking algorithm. And types of PV cells are like monocrystalline silicon, multicrystalline or polycrystalline structures, then thin film silicon, that is known as amorphous. And the combination of this also available, it is known as hybrid structures. So a monocrystalline silicon consists of cells so cut from the single cylindrical crystal of silicon. The main advantages of monocrystalline cells is their high efficiencies of about 15% or 14 to 15%, although the manufacturing process is complicated and expensive. And the polycrystalline or multicrystalline silicon, these are made from cells cut from an melted and recrystallized silicon. Here pure molten silicon is cast into molds, then sliced into wafers, doped and assembled. That is a manufacturing process. The polycrystalline is lower in conversion efficiency compared to the monocrystalline. Its efficiency is nearly 12% to 14%. And amorphous or thin film type crystalline. Amorphous silicon cells are made from silicon atoms in a thin homogeneous layer rather than a crystal structure. And this type of amorphous silicon absorbs the light from more effectively than crystalline silicon, so that the cells are thinner. So that amorphous silicon is also known as thin film PV technology. But the typical efficiency of this around 6%, but they are easier and therefore cheaper to produce. Some are flexible and are able to rolled and used for remote electricity generation. The flexibility of amorphous technology allows to be used in a wider range of applications. And a square foot of amorphous silicon average about 5 watts. Monocrystalline or polycrystalline average about 10 watts per square foot. So efficiency is a little lesser than that of a polycrystalline and monocrystalline. And hybrid structure, upcoming hybrid solutions are available now, like amorphous silicon plus crystalline silicon. Heterojunction solar cells are now become popular basically due to their excellent performance and simple low temperature production process. These kind of hybrid structure will combine both monocrystalline and thin film silicons to produce cells with the best features of both technologies. And its efficiency is also can be increased up to 17% in case of a heterojunction solar hybrid cells. And this is a schematic diagram of a solar photovoltaic systems. You can see that a solar array, then we need a inverter, in between a battery and battery required a charge controller. You can connect a DC load directly to the battery, and AC load is connected to after the inverter. So the solar photovoltaic systems mainly include batteries, battery controller, inverter, and mounting systems. And the photovoltaic array, as we discussed in a fuel cell, the modules wired together in a series to accumulate voltage, and the strings are wired together in parallel to increase the amperage or current. Collectively, they from the array. So you can arrange arrays in series and parallel manner. And you can see some manufacturers of PV roofing tiles have tested their products and meet the standards of Class A roofing using solar photovoltaic systems in order to reduce its. You can use a solar PV system as a for tiles and shingles. Manufacturers of PV shingles. Shingles is a roof covering that consists of individual overlapping elements. Have achieved a Class A rating by using a fire resistance underlayment and beneath the PV shingles. So it is this kind of arrangement reduces the space requirement of a solar photovoltaic system. So you can arrange it at the top of your roof itself in order to install the large number of photovoltaic systems. And batteries normally used, lead acid batteries are used for to store the photovoltaic generated electricity. Batteries are used in off-grid PV systems, although battery backup can be used in grid-connected applications. So without batteries, a grid-tied PV system cannot provide PV electricity when the utility grid is not energized. So it is battery is recommended if you are connecting into the grid. And battery charge controllers that are used to keep the battery charge levels in check. A charge controller is used in the PV system. That is controller will allows the charges below the or it maintains the state of charges SOC within the limits. The battery charge controller prevents the overcharging. So many controllers also protect the battery from over discharges as well. And we are using a PV inverter in that system. The PV array, batteries and charge controllers all function on a direct current. And most of our household appliances run on alternating current. So inverter changes the direct current into alternate current at 50 Hz. So these are some of the pictures of PV inverter. The sine wave inverter is for on-grid tied system. A look inside an inverter using installation process. A picture is shown here. And mounting systems, you can mount the PV systems in a different method, in a different way. So PV modules can be mounted directly on the roof. In many cases, specialized roof racks lift the array from the roof deck, allowing air to circulate under the modules. Many PV systems are designed to withstand 80 mile per hour winds also. So these are some other type of pictorial representation of the PV installation. PV systems can also be mounted on the ground using customized racks, or they can be mounted on the poles. So, and another kind of distributed energy resources is small scale hydroelectric power generation. The small scale hydroelectric generators are effectively used for generating power on site in microgrid. Extent of generation depends upon the topography of an area and its annual precipitation. This kind of generators suffers from large variations in generation due to the variable water flow caused by uneven rainfall. This is particularly true for hydro power station which do not have their own storage reservoirs, and for which the catchment area is spread over a rocky soil without any vegetation cover. So variable water resources also leads to varying the generation with a low capacity factor. So in this kind of small scale hydroelectric power generation, this requires this is depending upon the site. We need a water head in order to produce the power from the hydroelectric power generation. So power out from the hydro turbine is this have many advantages. Mostly this is in small scale, so minimum environmental impact, but it is site specific. You must have a resource, you must have a water resource and a corresponding head to generate the small scale power generation. It is very affordable and it can produce the continuous power supply. You can see one of the small scale power generating pictorial picture. We don't need a river for this. Just some falling water head is required. That's all, because this is categorized under small scale hydroelectric power generation. You just need a small water head. You can generate your own power. The turbine can be used in a many type of in many forms. So you can use a impulse turbines, which is having impulse turbine. It is a Pelton type turbine for a high speed application, and medium head, if it's a medium high head you are using you can use a Pelton turbine. Then medium head you can use a cross flow multi-jet Pelton turbine, and low head you can use a cross flow type. You can use the reaction turbines for medium head. That is one kind of reaction turbine is Francis turbine. For a low head you can use a Kaplan type reaction turbine. So these are the pictures of a Pelton turbine and turbo runner, etc. Pelton turbine, etc. And these are the some of the pictures of Kaplan turbine and Francis turbines. And reaction turbines you can submerge it in the flow. This is driven by the pressure difference. And the turbines are turned by water, as you all know that the turning motion drives generate the generator which produces the electricity. And the gross power equation for hydro turbine is given by P equal to QH eta rho g, where P is the power output, Q is the water flow rate, which is in meter cube per second, then H is the effective head in meters, eta is the overall efficiency, and rho is the water density, that is 1000 kilogram per meter cube, and G is the acceleration due to gravity. So that equation in fact shows that the power output can be increased by increasing the both effective head and water flow rate. So it is greatly depending upon the head and flow rate. And you know that penstoke, which is the pipeline through which water is brought into the turbine, and the cross section of the penstoke is suitably designed for optimum water flow rate. And various types of water turbine are used depending upon the water head and flow rate that we already shown. reaction turbine usually operate at lower head, example Francis and Kaplan turbine, and the impulse turbines, example Pelton wheels and turbo turbines, which are operate at higher heads. And the reaction turbines extracts energy from pressure drop overseas. Impulse turbines extract power from the kinetic energy of the water jet at atmospheric pressure. Power output can be increased by increasing the both effective head and water flow rate. So this is what is about small scale hydroelectric power generation and solar photovoltaic systems.